So far, we've covered, a bit about hypothesis testing and the general sort of approach to testing hypotheses, and then we sort of brought that together into doing what we call a one-sample test. So if you have a single sample and you want to test that against a known population value, we can do that. It's actually a fairly straightforward thing to do. But that's a fairly limited hypothesis. It requires that you know something about the population. It requires that you at least know the population mean. Oftentimes, we don't even know that, and it's not a very useful hypothesis in most cases. More common are we have two different samples and we want to compare them, and we can have two different samples. In two different ways. Either the samples are related to each other, they're we call it correlated samples. So you can see this when we are testing hypotheses about two related samples. You oftentimes will see it called dependent samples. It's oftentimes also called matched pairs. It's called within subjects, repeated measures. Lots of different names that refer to the same thing. Where essentially we're looking at either comparing two sets of people that are related. They could be siblings that are sort of assigned to different groups. More commonly, though, it's the same group of people that are being compared in like a pre-post test kind of thing. So where you have a group of people, you give them a pre-test, you do something to them, give them a treatment, have them participate in some kind of experiment, and then you then post-test them to see if there's a change. And that's sort of typically that's going to be a more common use of a related samples test. But the good part is it allows us to test hypotheses and address things that we typically can't address with just a single sample. So let's dive into what this is. And this is not a very complicated type of hypothesis test. Matter of fact, it's actually just going to rehash the one sample test with just a slight change. So let's talk about it a little bit. So again, this is called by many different names: related samples, matched pairs, dependent samples, repeated measures. There's all kinds of names for this kind of test, and it applies to all kinds of different stuff. So we're going to talk about what makes samples related or matched. We're going to talk about sort of, how do we use this idea of a difference score, right? So, something we can't do with either one sample or independent samples is we can actually subtract the scores across time. We're going to go through an example, and keeping with the drug theme from the hypothesis testing lecture, I'm not going to try to sell you drugs this time. I'm just going to talk about the effects of THC on memory as an example, and then we'll talk about how to do a t-test for this, like the formalized sort of process of testing for differences across related samples. We'll talk about some advantages and disadvantages of doing it this way. And then we'll revisit this idea of effect size and how we can look at effect size for repeated samples. Okay. So, as we said in the previous slides on hypothesis testing, these are the basic steps, right? So, and you've probably seen some version of this even in high school. When you've taken a science class, you probably went through some form of these are the steps to doing a research project, or to the testing hypotheses. I have them written out as these sort of say there's 1, 2, 3, 4, 5, 6, 7 steps, and you may have seen them as 5 steps or 8 steps. So sometimes things get broken out into different ways, but in general, it's these same basic steps. So we're gonna figure out and state what the null and alternative hypotheses are. We're going to decide on alpha. Now, this word, the word decide probably should be in quotes. We're not really going to decide on it as much as we're going to use what is the convention typically, which is 0.05. And again, you can use more strict versions of alpha, but if you go to 0.1 or 0.2 or some larger number than 0.05, you're not likely to convince very many people of significance in things. So, depending on the kind of data you have and the process in which it's collected, that's going to decide on the kind of test you can do. So far we've talked about a one sample z-test and a one sample t-test. So those are the choices. And today we're going to add to that a dependent samples t-test. So you'll now have sort of 3 different tests which to choose from, and it'll depend on the kind of data you have. Then we're going to talk about how do we find critical values, and once we have the critical values, how do we then state a decision rule? And the decision rule is something you come up with before you collect data, before you actually do the test, to decide what's going to lead you to believe or to decide in favor of the null or the alternative. And then once you actually do the test, you can compare that test to the decision rule and then make your decision. Okay? Remember, again, this is a class on decision making, not necessarily on math. This is how do we make informed decisions about data. Okay? So samples can be related for two basic reasons, right? They're in general. If you get specific, there's more, but in general, there's two reasons. First, they're the same people, right? So scores are going to be related because they're from the same people twice. This is usually either called repeated measures, or sometimes called within subjects. There's like a fly or something. Called within subject design, and it's fairly simple to think. If you do something and have me do a pretest of some sort, if I then come back and do the same test again, well, my response at the beginning is going to be related to my response at the end. So I can't treat them as sort of independent responses. I can't treat the responses as two different sets of independent samples. So we have to sort of address the fact it's from the same people and that those responses are related. Okay, so the second example, or the second reason, is that we can sometimes take people and either match them, which means we got to find qualities, things that other than the thing we're testing them on, we can find other things like age, education, gender, any number of things we can actually match them on to try to find people who are as similar as possible. And then we can match them so that any two people that are a match, then we're essentially going to treat them as if the response is coming from the same person, where one member of that match is going to be given one kind of treatment, they're going to be given a drug, or we're going to do something to them that is the treatment we're testing, and then the other half of the pair is going to not get it. They're going to be the control. So this is where the term sort of matched pairs comes from, and we're literally sort of finding pairs of people to match up. One of the most common versions of matched pairs that you'll see is when people do twin studies. So if you've ever seen studies where they take especially identical twins, and they'll use them to test something where one twin gets a treatment, the other twin doesn't. So you can imagine a scenario. Let's say given the current pandemic, let's say someone's trying to test a treatment for COVID-19. This is sort of a far-fetched scenario, but let's say you found, I don't know, 20 sets of twins, all infected with COVID-19. Well, you can give one set an active treatment, a drug to treat the disease, and then the other twin gets a placebo, and you see if there's a difference between their response. If all the twins that got the treatment get better, and the twins that get the placebo don't, then that's a pretty good way of sort of testing for the effectiveness, because the twins act as their own control. Genetically, they're sort of similar. Actually, not sort of similar. They're identical genetically, so it's a pretty good way of comparing. I wouldn't recommend doing that, because the people that are getting placebo, obviously, they're not going to get any better, which is oftentimes the ethical dilemmas of sort of drug testing and things, is that when you're testing out for the effectiveness of drugs, I mean, somebody had to go through the trial and not get the drug to see if the drug's actually working. Anyway, so this idea of sort of using twins, sometimes they'll use as siblings or sibling studies, even to like compare husbands and wives or partners, a married couple. Because people that are married are going to be more similar to each other than they are to other married couples. So any time where people have the ability to sort of influence one another and become related in that sense, you could then use them in a related samples or a matched pairs design. All right, so the picture up on top, since I just spent time trying to figure out what it is, it's from a movie called Duplicity, where Multiplicity. It's called Multiplicity, where a guy, this is Michael Keaton, who is the main character, he clones himself, and then one of the clones themselves, and then so you end up being ends up being a bunch of Michael Keatons running around in this movie. This idea that if we want to, if we have the same participant getting his data on two measures, it's sort of like, we're trying to clone ourselves in terms of comparing ourselves pre-treatment to post-treatment. That was sort of the tie-in to this multiplicity picture. But so repeated measures is this idea of literally measuring the same people repeatedly. So we're going to measure them on something. Let's say it's one of the things you might have thought of if you've gone through the IQ Plus lecture and talking about the one sample test, and something might have struck you even in the back of your mind, is that if I just take 25 people and I give them a drug and I test them at the end, it's like, well, we didn't know where they were IQ-wise beforehand, so how do we know they changed? So many people, their initial reaction is, well, why didn't we measure IQ first and then measure it again after treatment? So this is that kind of design where we want to know if there's a change in IQ from before taking IQ Plus, which is our treatment, to after. That would be that would make sense. It would actually be a way to test that. And there's some problems with that we'll talk about in a second, but that does seem to address this idea of, well, how do we know that they even changed? They may have been 106 beforehand and IQ Plus didn't do anything. So this is the basic idea behind a repeated measures version, dependent samples test. Okay. So another one, again, is this matched pairs. That picture came out better. There was a TV show a long time ago. It's called, I think it was Sister Sister or something like that. These twin girls here. This is the idea of sort of using a matched pairs design, is where you separate but matched on a set of criteria. So in this case, having two identical twins are going to be matched on most criteria. They're going to be the same age, the same gender. They're going to be basically genetically identical. So if I was to assign, to assign one of the twins to sample 1, the other twin to sample 2, I could then give one of the samples a treatment, the other sample would get a placebo, and then I could compare the two groups, and it would address some of the issues we have with doing pre-post testing, which we'll talk about in a second. But other versions of this is that they'll use siblings, sometimes cousins. They're trying to find people who at least share some amount of sort of common genetic material to sort of make them as matched as possible. But we even do this with sort of matched strangers. We'll take people who don't know each other at all. They share nothing. They no genetic material, no common upbringing, none of that stuff. But we just match them on a set of criteria. We find people that have the same IQ, same age, same whatever seems to be relevant in matching them. We can find people that are matched on a number of criteria. We'll assign one of those people to one sample and the other one to the other sample, and then we can treat them as a matched pair. And regardless of whether it's this sort of repeated measures version or a matched pairs version, what we're going to do with the data once we collect it is going to be the same. We're going to treat them the same way. So even though these two people, this says subject 1 in sample 1 and subject 1 in sample 2, even though they could be different, these are different people, two different twins or two different strangers or whatever it is, we're actually going to treat them as if they are the same person, and we're going to treat their data that way. So we're going to treat the data the same way we would if they were actually repeated measures designed with the same people. So how we collect the data may be a little different, but the way they get treated once we collect the data is actually going to be the same. It's going to be identical. So the reason why having samples that are dependent is sort of important, or it requires a different approach than when samples are independent, is that we're going to talk about this later on in the session, but their scores are going to be correlated. They're going to actually have a similar pattern where someone who scores high on a pretest is going to also score high, relatively high, on a post-test. So think about IQ. If I'm developing IQ Plus and I want to do a pre-post design, if I give people a pretest, and I'm expecting the IQ Plus is going to raise their scores, someone who's already high on IQ, they already have a high IQ, they're going to stay relatively high, right? So if you think about how people, wherever people are, someone who's high at pretest, right? Yeah, different people. So this is their pre-test IQ, and then you got a post-test IQ. It's likely that wherever this person is, they're likely, if they do increase, that's great. This person might increase a little bit more. This person might, decrease a little bit. But wherever they are, they're likely to stay roughly in a similar sort of pattern at post-test. So if IQ Plus does raise their scores, it's not like it's going to raise this person that was at the bottom to being at the top. It doesn't make any sense. They're going to stay in relative sort of rank order, where the highest people are going to stay relatively high, the low people are going to stay relatively low. So we can't just ignore the fact that there's this relationship between the two of them. There is the differences between people here that in a one sample test we treat as just sort of random, variation, just a standard deviation between people. Well, it's not random anymore because there's a similar variation at the post that we can sort of use to our advantage. So when we have pre-post tests like this, when we have a dependent samples test, we can't just ignore the fact that they're related. We have to actually address that, and which is actually a much easier thing to do than it will be when we actually go to treat them as independent in the next sort of lecture. The next topic, which is probably more useful, gets used more often as a research design, but it is a little more complicated to analyze. So this idea that because people are related, they're not independent. All right, so we're going to address this independence issue when we come to the independent samples t-test in the next section here. But however, the scores can, because they're related, we can manipulate them. What we can do, because they're related, is find a difference between them. Right? I can actually calculate a difference score. I can take post minus pre, or pre minus post, or whatever seems to make sense. And for every person, I can actually find, okay, well, this person, they went up 2 IQ units. This person went up 4. This person here went down 2, right? So we can actually figure out what the change in IQ is and figure out a difference, and then we're going to use this difference score as our data. That's what we're actually going to focus on for the dependent samples test. And because we're taking 2 samples, subtracting them and creating just a single set of scores, we're gonna analyze this in the same way we did the same way we analyzed a one sample test, because we just have one sample of different scores, and we can use that to sort of test our hypothesis. Different scores are exactly what they sound like. We're going to calculate the change from pre to post. We're going to take the difference, and it could be before, like pre minus post, or before minus after, if that makes sense. We can take after minus before, take treatment minus control, control minus treatment. And you're probably thinking, well, how do I decide which way to go? It oftentimes depends on how you expect them to change. Like with IQ, if I'm expecting the scores to go up, right, if everyone's supposed to go up in IQ, if I take pre minus post, I'm going to have a bunch of negative numbers, which is fine. There's nothing wrong with negative numbers. I'm going to have an average difference score that is all negative. In that sense, negative numbers actually represents a sort of positive change. It actually means they did go up in IQ. So it's sometimes hard for people to wrap their head around the fact that a negative number means that it was good. So I oftentimes will try to choose the order of the difference score so that the differences represent positive numbers. So in that case, if I was doing the IQ Plus study where I wanted people's IQs to go up, and so from pre to post I expect scores to increase, I would likely do the sort of after scores, the post scores minus the before scores, the pre scores, so that all the change, positive numbers, mean a positive change. That makes sense to me. It actually just aligns better in my brain to have positive numbers represent positive scores. So and if I was doing something like an intervention to reduce depression, right? So let's say new drug or something, some kind of I don't know, serotonin, something that actually is supposed to decrease depression. So you give people depression scores, right? They're all high at pre, and you're expecting their scores to go down. You want everyone's scores to sort of decrease, afterwards at post. In this case, I would likely then take pre minus post, so that the different scores, all the different scores, would be positive numbers, right? Because if I took post minus pre in this case, then they would be negative numbers, and negatives would mean positives, and that just, it starts to make your brain hurt a little bit. So if we can keep the order of the subtraction, the difference, so that the numbers and the differences actually represent the positive change we're looking for, it can work. So in this case, pre minus post makes sense because we're talking about depression and we want to lower depression. But with IQ, because we want to raise it, it makes more sense than to do post minus pre. But you got to keep track of what you're doing. Make sure that when you get the scores on the different scores, that they actually match up to your hypothesis and it actually makes sense. So the main thing here is that once we subtract the scores, pre minus post, post minus pre, whatever it is you decide on, we're going to base all the rest of the analysis on just those different scores. We're basically going to ignore the before and after data and focus only on the different scores, which means we're going to be back to doing a one sample test. So a dependent samples test and a one samples test are essentially the same thing. It's just the dependent samples test has an additional step, which is we're going to subtract the scores first, and then the rest of it's going to follow the same steps we did for a one sample test, which means it's a very easy, very straightforward test. Okay? I mean, relative to the rest of them that we're going to talk about. So let's talk about an example. So I was trying to think of an example that would be interesting and sort of at least somewhat relevant or whatever. And before I used to had an example that it was I think it was about baby food or something, I forget. But so I sort of switched a couple years ago talking about this. It seems a little bit more, at least a little bit relatively more fun. I don't know. So this example is looking at the impact of THC in recall. So just as a preface, this is not real data. I did not collect this. It is just a simulated sort of example, but it is based on at least some research that people have done and the findings they have found. So I'm not just making up the idea, but I did make up the data to sort of match what other people have found. So I didn't want to. One, I didn't want to use a huge data set, and two, I didn't want to just steal their data. So the question here that we're trying to ask, the main hypothesis is, does THC, this tetrahydrocannabinol, does it actually impact memory? And you've probably heard, news or at least in social media, sort of clickbait and stuff that, the impacts of marijuana on memory, and I mean all kinds of stuff. People are that have done research into this, and especially around the legalization of it and all kinds of stuff, and people arguing all kinds of things. So there's lots of research, some good, some bad, out there on sort of the relationship between the impacts of THC and things like memory. So the way this study could be set up, and again, this is made up, but this follows a similar kind of thing, is that in step one, I'm going to find 10 low to no use respondents. Okay, meaning that I'm not going out there and finding people who regularly ingest THC in some way, whether they're smoking it or eating edibles or whatever it is. These are people that don't regularly use or ingest. And I'm going to give them a recall task. So they're going to come in, and step one is I'm going to give a recall task. So they're going to be shown a list of 50 words. And these are all sort of simple words. Nothing too, these are not like complex 7-syllable words. These are all sort of fairly simple, common words. And they're going to look at they're going to give a certain amount of time to sort of study the word list. Then they're going to be given a distractor task. So a distractor task could be any number of things. People use all kinds of things in research. They'll have them do some math problems, or they'll have them color or whatever. They do something that is supposed to get their mind off of the facts, so they're not just sitting there and rehearsing the 50 words. And then the post test is going to be they're going to be given. So they're going to do the distractor task, and then they're going to be given the real test, the real pre-test is they're given a recall task. So then that could be, again, done in any number of ways. It could be that they're just asked to write down as many of the words they remember as possible. They could be shown a list of words and have to identify which ones are in the list and which ones weren't. All kinds of stuff. So the trick is, once they actually do the recall task, they then get scored so that they get a point for every word in list one that they remember. They lose a point for any time that they write down a word that wasn't in the list. So they somehow remember a word that wasn't there. So they can actually lose points for that. And in the end, they sort of add up the number of questions that are words they recalled correctly minus the words they recalled incorrectly, meaning it was the wrong word, and they get a score. They get sort of a recall score. So that's sort of the step one is sort of the pre-test. Okay. Step two, they're given a Rice Krispie square, like these ones up here, with I don't know, like 15 milligrams of THC. So this is not a crazy dose, but for someone who doesn't use, 15 milligrams is a fairly high dose for someone who's a low to non-user, at least according to the resources that I looked up at the time. So so that's the sort of treatment. So they're going to ingest THC, and then they're going to ingest THC, and then they're going to wait a couple hours. Right? So 2 hours go by. Now they're going to be shown a new list. This isn't the same list of words from the pretest. It's a different set of words. They're shown these 50 new words. They're given a similar type of distractor task, and then they're also then given a recall task. So again, if every word that they get correct, they get a point for it. If it's a non-list word, then they lose a point. But if they recall a word from list one, right? So if they mistakenly pull a word from the first list, they don't get the same negative. So they don't lose a point for that. It's just sort of a wash. They recall the word from the previous list. It doesn't count towards this recall task, but they also don't lose any points. Right. So that's the basic thing. They do a sort of recall task. They ingest THC and they wait for it to sort of make sure it kicks in. So they wait a couple hours because when ingesting THC versus smoking it or other means, it takes a little bit longer to sort of hit your bloodstream. So they wait a couple hours. They then repeat the same task with different words, and then they want to compare the recall before and recall afterwards as a pre-post dependent samples test to see if THC really does affect their memory in this second run. Okay. So we can think about the null alternative to this in a couple different ways. So one, it's like, all right, so if I think that THC is going to impact memory, then I would expect that the post-recall, right? So this is the alternative. Now you may be thinking in your mind or in your experience, that THC doesn't impact memory. It's all sort of BS or whatever. But that's not a research hypothesis. So to sort of show that there is no effect, it's not oftentimes what we test. That's usually left to the null. So for testing this hypothesis that THC does impair recall, I would expect scores in the post-test, the recall scores, to be lower. So in that case, looking at the alternative, this H1, I would expect pre-recall, the average pre-recall for these participants to be higher. All right, so we're going to get a higher pre-recall versus the post-recall. All right, that's great. And that means the null is going to be, well, if there's no difference, they're going to be equal. People are going to remember the same amount of words either way. Or it could go the other direction, where for some reason people's pre-recall is worse than post-recall. Like somehow the THC helps their memory. They actually remember things better at post, and people end up scoring higher. That would be sort of the opposite of what the research hypothesis is. The problem here, though, is that this is still sort of dealing with two separate means, right? There's a mean for pre, a mean for post, and we just talked about that. I don't want that. We got to sort of convert this over to thinking about this as a one sample test. So in reality, this approach to this is not going to work very well. This is not what we want to do. We don't want to sort of hypothesize this in terms of two different means and how they compare. All right, so we know we're going to be taking differences, subtracting things. So why don't we go there? So if I take pre-recall, again, we expect to be higher. So pre minus post should be a positive number. It should be greater than 0. So if I recall more things at pre than I do at post, and I subtract pre minus post, I should expect positive numbers. So that's why it's greater than 0. Then the reverse of that, the opposite, the null hypothesis would be that if I take pre minus post, it's either going to be 0 because they're remembering about the same, or it could, again, if they remember more at post, that's going to go against the research hypothesis, and we're going to get a less than 0 for the null. So that's a step in the right direction. We're now talking about subtracting them, but we're still dealing with, you know, two different means. We're taking the mean of pre and the mean of post and subtracting them. I don't want two separate means involved. So even though this is in the right, you know, right direction, it's sort of thinking about it in, you know, in a correct way. We still want to get it down to just one mean. So we're not going to be subtracting means, which is what this shows. We're actually going to be subtracting scores. So here, this is just a different way of thinking about it. This is the same thing, but I got a single mean for both, a single mean for each hypothesis. So I'm going to take each person's pre-recall score, and I'm going to subtract their post-recall score. So I'm doing this for every individual participant. And if I look at that, the mean of those differences is going to be just a single mean, which is what I want. I want just one mean of the differences. So this is this version sort of matches up to what we're going to be doing in terms of the test much better, because I don't have two means. I'm going to have one mean of different scores, which is what this is showing. One mean, and it's showing the same thing, that if I take individual pre-recall scores and subtract the individual's post-recall scores, I should have a value that is greater than 0 if the alternative is true. If people's pre-THC recall is higher, subtracting pre minus post should give me a positive number. It should have a positive, an average positive difference. So this is a better way of thinking about it, and I do want to, you know, make sure that these are sort of going in the right direction. That I am thinking about this as greater than because of the order. If I had flipped them, if I had done, if I had chosen to do, you know, post minus pre, totally fine to do that. There's nothing wrong with taking post minus pre. It's just that I'm now going to expect a number that is less than 0. I'm now going to be expecting a negative number. So all the differences, if this is true, I should have an average difference score for every person to be a negative number. Totally fine. It's just, again, we're going to be dealing with all negative numbers and dealing where this one is dealing with the potentially the positive side of a distribution like this, right? Everything's positive. This one is doing the exact same thing. It's just we're going to be on the opposite end of the distribution. I'm going to be on the negative side looking for differences. So that's in the way. But you get the idea. It's sort of, we're going to be in this side of the distribution instead of the positive side. And people in general, this may not apply to you, but people in general tend to find dealing with the positive side a lot more comfortable, right? Dealing with positive numbers. Because you have to think about, here, I need to find, to reject the null, I need to find a number that is just larger, and a larger value. Here, I need to find the value that is more negative. It's farther out in the negative, and people just oftentimes will make more mistakes there because they'll find a number that is more positive and think that that's bigger, and they'll confuse their decision rules and stuff. So sometimes it's easier just to deal with the positive numbers. So if you can arrange it so that you're subtracting in an order that creates positive numbers, and that represents your hypothesis, that's going to be a lot easier to deal with. So once we have this sort of process, and notice I haven't even shown you the data or anything yet, because really most of this stuff, most of the process of the sort of 7 hypothesis testing steps can and should be done before you even collect data. Right, because it should be done, and the word that gets thrown around a lot of people like to use in terms of this stuff is that your hypotheses should be a priori, which is just a Latin for like prior to, beforehand. So your hypotheses and all that stuff that you're setting up here should be done before you even start your research project, before you even start collecting data. Most of this stuff can be done before that. So if I'm testing for recall and THC's effect on recall, well, I should be able to do at least up to my decision rule. So step 6, which is doing the test I can't do, and my decision I can't do. But steps 1 through 5, I should be able to do beforehand. So we already figured out that these are our null and alternative, right? The alternative is saying that I think that pre-recall minus post-recall is going to give me a positive average. An average is going to be a positive number. So the null then is just the opposite. Now this is actually something that I should mention, and I may mention it a couple times, is that even though the 7 steps are written this way, we're supposed to state your null first and the alternative second, it oftentimes is easier to try to state the alternative first, because it's the thing that you're trying to test. It's the thing that in a practice problem we're on a test is stated. I want to show that THC lowers recall. All right, that's an easy thing to sort of think about. All right, if it's lowering recall, what does that mean? All right, well, pre-recall minus post, that means it's going to be a positive. Right? I can think about that very clearly and sort of write that out, and then I can decide what the null is by just thinking, okay, what's the reverse of that, and then writing that out. And just to make sure that the null is the one that always includes the equal sign. So as long as you sort of have these going opposite directions, and you have the equal sign sort of placed with the null, then you probably got it covered. So sometimes it's easier to start with the alternative, even though it's technically listed as the second thing. You might want to go there first, go back to one, and then do the rest. So I haven't stated anything about wanting to change the alpha level or do something at the more strict level. So we're going to stick to the convention. And I keep saying it's convention because there's lots and lots of debates been going on for quite a while about whether 0.05 is even meaningful, why we use it, but it's still something we've stuck to. Someone at some point decided 0.05 was the thing, and it has stuck around. It's become the convention. So we're going to assume when we're talking about, not 0.5, 0.05, that when we're talking about our alpha level, when we're thinking about, looking at the previous lecture, when we want to decide how unlikely something is. So if we get a result for our alternative here, and we want to know, could we have just got this difference in recall by chance? Well, this 0.05 is us defining what we mean by chance. So if you're getting differences by chance, it means that if you did it over again, you would get similar types of results. So we want to know if our result is somehow unusual, and it's that unusualness, the unusual quality of our result that's going to lead us back to thinking that our alternative is true, and sort of giving some evidence for this. Right? So when we say unusual, well, what do we mean unusual? Well, it means it has to have a less than a 5% chance of occurring all by itself. And if it has a less than 5% chance of occurring by itself, then that's fairly unusual. So we have this thing. We're expecting, like, if there's really no difference between pre and post recall, we expect to get a 0. But we know from experience and from other things and from research in the past that even if if THC has no impact, we're not going to get exactly 0. People aren't going to remember the exact same number of recall words from two different lists. Sometimes they'll remember more from one, sometimes they'll remember more from the other, and there's going to be some flip-flopping. So sometimes you're going to get samples that are a little bit higher, sometimes samples are going to be a little bit lower, and they're just going to sort of randomly vary somewhere right around 0. And it's really going to stretch the whole range of this. But as you get farther out into both sides of this, these results are going to get fewer and fewer, less likely, and we know that because of the distribution. We know that as we sort of go out into the tails, the probabilities for the values out here in the tail are a lot lower. So if I want to know if I take just I happen to have one sample that I'm using and I gave them THC, and I want to know, is this one sample unusual or unlike the rest of these sort of random distributions, I have to define what I mean by unusual. So the conventional definition of unusual is that it has to have a 5% chance of occurring or less. So it means that our distributions or our sample has to be somewhere over in this tail. If I'm doing a one-tailed test, it has to be somewhere over here in this 5% region. And if it is, then random chance is not a very good explanation for how we got that sample. It's more likely that the sample is out here because of the THC, because of the fact that the THC actually moved them up there. Okay, so this is the same. I'm just rehashing what we talked about in the sampling distribution hypothesis testing stuff. Just rehashing it. That's where this 0.05 comes from. Is basically our definition of what we mean by unusual. All right. It is statistically, probabilistically unusual to get a sample that size, that has a 5% chance or less by chance alone. So chance is not a very good explanation. A better explanation is that the thing we did to them worked. In this case, it's THC worked to lower their recall. All right. So, all right. So that's a rehash of alpha. Why it's 5%, I couldn't tell you. I'm sure there's probably a good explanation, and I'm sure I've heard probably 10 different explanations of why it's 5%. But it doesn't matter. It's just what it is. It's convention. So then we got to decide on the type of test. So we know, obviously, this is a dependent samples t-test, or dependent samples test lecture, so that's obviously the test. But in thinking about it, so far we only have 3 choices. It's either going to be a one sample Z test, and for it to be a one sample Z test, there's certain things I have to have. For a one sample Z, I have to have both the mean of the population and the standard deviation of the population. I don't have either one of those. Right? I don't even have a population. I'm not comparing this to a population, so it's not going to be a Z. If it's a one sample T, well, I still have to have the population mean, which I haven't supplied. So it's not going to be a one sample test either. So obviously it's not either one of these things. It can't be either one of those. So the third test that we are now talking about here it's going to be our dependent samples T. Now you might be thinking, well, why not a dependent sample Z? Because we talked about a one sample Z and a one sample T. Well, in a one sample Z, again, we were supplied with the population mean and population standard deviation. It's not likely we're going to be given a population standard deviation of different scores for recall. Like that's not a very likely thing. So the Z test we talked about first as a way of introducing this idea of testing one sample versus the population. But in practice, t-tests are what you're typically going to be doing. So I'm not going to pretend like that you're going to come across a dependent sample Z. So I'm not even going to talk about it. So we're going to focus directly on a dependent samples t-test, where you need to actually use the sample standard deviation to compute the test. So we're going to just skip right into that because that's the more realistic sort of version. So now we need a decision rule. Okay, our decision rule we can't quite, at least not make totally specific yet, but what I want is something like this. If, this is like the generic version, if my T observed, TO, is greater than, and why greater? Because I'm hypothesizing that it's going to be, I have a greater than in my alternative hypothesis. Right? So I'm going to stick with TO is greater than my T critical, TC, so I'll say T crit, then I'll reject the null. That's sort of what we want to set up as our decision rule. If my T observed, my comparison between my T observed and T critical seems to match the alternative here, my T observed is larger than T critical, then I reject the null. I'm then going to go on to do the test and then compare that back here. So we have 10 people, so we can actually figure it out. Let's figure out the T critical real quick. So instead of just saying T critical, let's figure out what is T critical. I can figure out T critical here with, now T critical always has, when it's a one sample or dependent samples, because they're essentially treated the same, T critical is going to have an n-1 degree of freedom. So I need to look up T critical with n-1, and I can go to the T table that is on Canvas. Scroll down to here, and let's say I'm doing this as a one-tailed test. I know that because of the way I did my hypothesis. It's directional, right? So I'm saying I think recall pre is going to be greater than recall post, because when I subtract them, I'm going to get a number greater than 0. So with that being said, I'm going to do a one-tailed up here, one-tailed 0.05. Okay, So I'm going to scroll down to 9 degrees of freedom. So 0.05, one-tailed, 9 degrees of freedom, because I have 10 subjects. So with 9 degrees of freedom, my t-critical is 1.8331. So this is from that t-table. So my decision rule really then, specific to this problem is if my t observed is larger than 1.8331, I'm going to reject the null. This is a positive number, right? So t observed needs to be greater than a positive because I'm only interested in the positive side. And that's because of the way I set up the pre-recall versus post-recall. I'm expecting it to be a number larger than 0, a positive number. So if my t observed is larger than 1.8331, notice I'm not putting the absolute value here or anything. It has to be a positive number that is larger than the positive critical value.